In this lesson, we're going to talk about simplifying radical expressions. Let's start by just putting a couple of things down the far right side of your paper. 2 squared we know is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 is 49, 8 is 64, 9 is 81, 10 is 100. Now we're talking about simplifying radicals. If you recall, I've mentioned many times that subtraction undoes addition, division undoes multiplication, a radical undoes raising something to the power of 2. So if I take the square root of 4, which you already know is 2, the idea that is I am undoing the exponent of the base, and so that's why it returns a 3. So the square root of 9 is 3. The radical undoes the exponent, whatever the base was raised to, and so it returns the base. And so this is what we're going to be looking at. So if I have the square root of 4, we know that that is 2. But if I have the square root of 8, what you're going to be asked to do is, I can't put this in the calculator and write the number, it's going to be 2 point something or other. You're going to be asked to keep it in radical form. So I need to look for the largest perfect square inside of 8. So we have to look at its factors. And so you need to look for the largest perfect square factor. And so we're going to use this list that we generated over here to find the largest factor that's a perfect square in our number. In 8, it's 4. So I'm going to take the square root of 4, which is 2. So we write that on the outside of the radical. And since 2 is not a perfect square, he's going to get left behind. Let's take a look at the square root of 10. We have the factors of 2 and 5. And unfortunately, M1 and 10, none of those are perfect squares. So he is considered simplified. So we can't do anything with him. Let's take a look at the square root of 12. Again, we're looking for the largest perfect square. So if I look at 2 and 6, that's not helping me at all. But if I look at 4 and 3, we can see 4 is the largest perfect square. So I take the square root of 4, which is 2. So he comes out of the radical. And I'm going to leave behind the 3 because he's not a perfect square. So 2 root 3 is the final answer. This does say 2 times root 3. This is multiplication because of the idea of exponents as being a form of multiplication. All right, let's take a look at the square root of 15. If we look at its pairs, we have 3 and 5 and 1 and 15. None of them are perfect squares, and so the square root of 15 is simplified. Let's take a look at the square root of 24. Lots of possibilities. We have 1 and 24, we have 2 and 12, we have 3 and 8, and we have 4 and 6. And I always recommend looking at all the different pairs that are possible, because here we can see a perfect square, which is tucked inside of this 8. All right, and so if I tried to go with this pair, I would not see the perfect square. But the perfect square is 4. So I'm going to take the square root of 4 times 6. The square root of 4 is 2, so he comes out. 6 is not a perfect square, so he's going to stay behind, and he is simplified. Let's take a look at some more examples on your worksheet. Let's take the square root of 28. Let's think about his possibilities, 1 and 28. We have 2 and 14, and we have 4 and 7. We can see a perfect square here, so we're going to look at 4 and 7. The square root of 4 is 2. He's not a perfect square, so it is 2 root 7. Reminder, just a quick reminder, because I'm going to need that shortly, it's 2 times root 7. This is simplified. Let's take a look at 72. Now, think back about our list here. You want to find the largest perfect square. Yes, 4 is a factor of 72. 9 is also a factor of 72. 16 is not, and 25 is not. But interestingly enough, if we look at all the factored pairs, 36 is a factor of 72 by 2. Okay, I want to look for the largest one, and I'll show you in a moment why. Can't take the square root of 2, but I can take the square root of 36, which is 6. And we have root 2. So that is the simplified answer. Now, oftentimes we think about 8 times 9. Well, 9, yes, is a perfect square, so we would have 3 root 8, but 8 has a perfect square in it also, which is a 4. So I'd have to do this process again so I could take out the square root of 4. And if I take out the square root of 4, then I have to multiply it by the 3 and leave that 2 behind, and I still get the same answer. But if I look for the largest perfect square from the beginning, then I don't have to do this process a second time to know that it's simplified completely. Now, when we look at radicals, radicals are a form of multiplication because of the exponent. And so I can multiply two different radicals together by putting both of those values underneath the radical. So I get a root 20 as my expression, but I still want to simplify it. So I'm going to look for the largest perfect square. So 2 and 10, there's no perfect square there, but we can see with 4 and 5, we have our perfect square. So I'm going to take 4 square root of 4, which is 2. Not a perfect square, so he stays behind. So 2 root 5 is the final expression. So I can bring these together. Now remember, this is 3 times root 5. I cannot multiply outside numbers with underneath numbers because they're not the same type. The square root of 5 is going to be something between the square root of 4, which is 2, and the square root of 9. It's going to be very close to 2. So I can't multiply outside numbers with inside numbers, but I can multiply these two together. So I have 3, and I can bring those 5s together underneath the radical. So we can see I have 3 root 25. 25 is a perfect square. We can see I have 2 5s underneath there. So I'm going to take the square root of 25, which is 5. Remember, this is multiplication. So, whoops, final answer is 15 simplified. So we always have to make sure, even though these are both simplified by themselves, because I can multiply them together, in this case, we're creating another root. Same thing here, both expressions being multiplied together, but they're all being multiplied. So I can take 2 times the 3, which is 6, and I can take 3 times the 15, which is going to give me a 45. So we know that we used 3 times 15 to get the 45, but I want the largest perfect square. 45 is the result of 9 times 5. So I'm going to use that because here's my perfect square. Take the square root of 9, which is 3. That 5 stays behind. I'm going to multiply 6 and 3, which is 18. So 18 root 5 is the final answer. Now, what happens if I have a variable underneath the radical? Now remember, I can square variables, right? So this x squared is a perfect square, right? It's x times x. We know it's a perfect square. So the square root of x squared is actually going to be x. Remember, that was x raised to the power of 2. So I'm returning the base in the same way that I had 2 raised to the power of 2 and I returned the 2. X raised to the power of 2 returns an x. What if I have an x cubed? Well, I'm only taking the square root of it, but remember, x cubed, if we use our exponent rules, is x squared times x. So I have a perfect square in there in x squared. So I'm going to take the square root of x squared, which is x, but since he wasn't perfect, he's going to stay behind. How about x to the 4th? X to the 4th is x squared times x squared. They're both perfect squares. I have 2 perfect squares in there. So I'm going to get x times x, which is x squared. Okay, because I took the square root of x, which is x, square root of x squared, which is x. How about x to the 5th? And then let's see if we can find a pattern. X to the 5th is x squared times x squared times x. Do you see how I'm growing here under the radical? Square root of x squared is x. Square root of x squared is x. Can't take the square root of this guy, so he's going to stay behind. So we have x squared raised, or root x. Let's try one more. X to the 6th. If you think about it, there are 3 x squares in there, right? X squared times x squared times x squared. And so there's one more extra guy in there. So when I take the square root of that, I have taken 3 of these out. So we have x cubed. Can we see a pattern forming here? One of them gave me x. Here I had that spare guy, so he stayed underneath, but I still had that one from the previous one plus an extra. Here, x to the 4th, I ended up with x squared. Half of those that were under the radical, x to the 5th, we have that same x squared from the previous one, but we added on one more. X to the 6th gave me x cubed. So you should start to think about, oh, well then x to the 7th must mean x cubed plus an extra one here. So what is the shortcut rule? I'm going to take what's under the radical. So for instance, x to the 5th. I'm going to take that 5 and divide it by 2. Because if you notice, half of them came out. I get 2.5. And so I'm going to take out 2 of them, x squared, but since I have this little point piece, this little remainder, he stays underneath the radical. Let's try x to the 9th. If I take 9 and divide it by 2, that gives me a 4.5. So I'm going to have x to the 4th. There's that partial piece. So I'm going to have one guy left behind. So because it's odd, I'm going to have one left behind. So when I have an odd exponent, somebody's always going to be left behind. All right, I'll take them out in pairs, but one guy will always be left behind with an odd exponent. Let's try a couple. So looking at 81 is a perfect square, so we know that that's a 9. C squared, it's even, so they're all going to come out by half. So 2 divided by 2 is 1, so I'm going to take one of them out. D to the 4th is even, so we'll divide that by 2, so d squared, and he is simplified. None got left behind because they were all even. Let's try one more. Square root of 75, so this is 3 times 25, right? So the square root of 25 is 5. So we know that the 3 is going to stay behind. Let's take a look at this guy. 5 is odd, all right? So I know that I'm going to have an odd m behind because of the odd exponent. Divide 5 by 2, which gave me the 2.5. So 2 m's are going to come out, but because it's odd, one guy stays behind. The odd man stays back. 2, or n to the 2nd power, 2 is even. So if I divide 2 by 2, I get 1. So one of these is coming out. He is in simplified form.